Hi, this is Alex from devstories.eu. Astropy, Python for Astronomy, Episode 6 of 15. Searching a massive catalog for a specific source usually means executing a full linear scan that eats up processing time. But if you structure your data properly, you can reduce those lookups from minutes to milliseconds. That is what we are covering today: advanced table operations, masking, and joins. Astropy tables are not just arrays. They act as an in-memory relational database that natively understands physical units. Suppose you have a photometric catalog and a spectroscopic catalog, and you need to combine them based on a shared source ID. Before you merge them, you have to handle missing data. Your photometric catalog likely has missing magnitude values because an observation failed or a sensor dropped a frame. You might try to filter out those missing values using standard NumPy Boolean arrays. Do not do that. Standard NumPy masks applied directly to a unit-aware table will silently strip away your physical units and break mixin objects. Instead, Astropy handles this with the masked column. When you work inside a QTable, which is the unit-aware table class, Astropy automatically uses masked column operations under the hood for missing data. This ensures your magnitude column keeps its physical units intact while safely marking the missing entries so they do not corrupt your downstream calculations. With your cleanly masked photometric catalog ready, it's time to combine it with your spectroscopic data. Astropy provides a join function that works much like a relational database. You pass the function your left table, your right table, and specify the shared column name as the key, which in this case is your source ID. If you specify an inner join, the function evaluates both datasets and returns a new table containing only the rows where the source ID exists in both catalogs. Here's the key insight. Because you are using QTable objects, the join operation automatically reconciles and preserves the units from both sides. Your merged table will contain the precise physical parameters from the spectroscopic data alongside the properly masked magnitudes from the photometric data, perfectly aligned. Now you have a merged catalog, and your analysis requires pulling the exact parameters for one specific source ID. Without intervention, finding a row in a massive table requires checking every single entry sequentially. Astropy solves this performance bottleneck with table indexing. You can instruct the table to create an index on your source ID column. Behind the scenes, Astropy builds a B-tree data structure mapping your source IDs directly to their underlying row locations in memory. Once the index is built, you retrieve your data using the table.location property, passing in your target ID. The engine traverses the B tree, skips the full scan entirely, and fetches your row in logarithmic time. You can even index multiple columns simultaneously to handle complex lookups, such as finding a row by both source ID and observation date. Building an index takes a fraction of compute time up front, but it pays off immediately when you need to run repeated lookups across heavy datasets. The true power of Astropy tables is not just storing data, but maintaining the physical integrity of your units across complex relational joins and high-speed B-tree queries. That's all for this one. Thanks for listening, and keep building.